From Waterloo's tech sector, which could have big implications, a team is banding together in a new nonprofit to build what's described as the world's first open-source quantum computer.
Now, the latest development from Google that it describes as a state-of-the-art quantum computer chip.
NASA, the agency that dared to reach for the stars, has made a chilling decision. They've pulled the plug on their most ambitious project, a quantum computer poised to revolutionize science. Was it a breakthrough? A terrifying discovery, or something far more sinister? Did they unlock the secrets of the universe, or unleash a force beyond their comprehension? Whispers of a catastrophic failure, of unintended consequences, and a chilling truth hidden beneath the surface are swirling among the scientific community. Now, a lone ethical hacker claims to have uncovered the real reason behind NASA's silence, and the truth he reveals is far more unsettling than anyone could have imagined. This isn't just a story about technology. It's a chilling tale of ambition, fear, and the terrifying potential for human ingenuity to spiral out of control. The basics of quantum computing. Quantum computing is a revolutionary leap in computation that leverages the principles of quantum mechanics to process information in ways that traditional computers cannot. Unlike classical computers, which use binary bits, zeros, and ones to encode information, quantum computers use quantum bits, or qubits. Qubits can exist in a state of superposition, where they represent both 0 and 1 simultaneously. This unique property allows quantum computers to perform multiple calculations at once, vastly increasing their computational power for certain types of problems. Another fundamental principle of quantum computing is entanglement, where qubits become interconnected in such a way that the state of one qubit is directly related to the state of another, regardless of the distance between them. This enables quantum computers to perform complex computations with unparalleled efficiency. Additionally, quantum interference is utilized to amplify correct solutions while cancelling out incorrect ones during calculations, making quantum algorithms extraordinarily powerful compared to classical methods for specific tasks. The capabilities of quantum computing are unparalleled in so many areas. As an example, NASA is examining the use of the system to improve spacecraft trajectories and to simulate very complex systems like propulsion mechanisms, as well as massive datasets produced by telescopes and planetary rovers. NASA worked with D-Wave and Google in the deployment of systems like D-Wave 2X, one of the first uses of commercial quantum systems in scientific research. These applications are beyond the reach of classical computers, which makes quantum computing a powerful tool for solving problems that were previously considered intractable. This technology also plays a critical role in advancing machine learning, cryptography, and material science. Despite its promise, quantum computing is still in its developmental stages and faces significant challenges. High error rates, environmental decoherence, and the complexity of scaling systems with large numbers of qubits are among the obstacles researchers must overcome. However, organizations like NASA, in collaboration with industry leaders such as Google and D-Wave, are at the forefront of addressing these challenges. For example, Google's Sycamore processor demonstrated quantum supremacy in 2019 by completing a task in 200 seconds that would take the fastest classical computer thousands of years. By refining quantum algorithms and improving hardware, they aim to unlock the full potential of this groundbreaking technology, paving the way for a future where quantum computing becomes an integral part of scientific discovery and innovation. Yet, beneath the promise of quantum computing lies a story that raises unsettling questions, one that NASA itself couldn't ignore. Unveiling the mystery. In a surprising turn of events, NASA abruptly shut down its quantum computing system, sparking widespread curiosity and concern. Officially, the organization cited unexpected results during a routine test as the reason for halting operations, claiming the decision was necessary to investigate anomalies thoroughly. However, whispers of a deeper and more unsettling truth emerged when ethical hacker Ryan Montgomery stepped forward. Montgomery revealed that NASA's quantum computer may have inadvertently breached top-secret encryption systems, accessing classified data that was never meant to be unlocked. This revelation raised alarms about the potentially uncontrollable nature of quantum technologies. Montgomery's investigation uncovered that NASA's quantum computer, while conducting encryption simulations to test quantum-resistant security measures, performed an unintended computation. This included bypassing encryption techniques that protect government databases, a task traditionally believed to require decades for classical supercomputers. This computation reportedly bypassed multiple layers of encryption, granting the system access to government databases containing highly classified information. According to Montgomery, the incident highlighted the unpredictable power of quantum computing and its potential to become a tool with catastrophic consequences if not carefully managed. The system, which was originally designed for scientific research and mission optimization, suddenly revealed a darker side: its capacity to dismantle current encryption protocols at unprecedented speeds. Quantum computing compatibility is one of the only ways to facilitate an impressive number of spheres. For instance, quantum technology is an area of active research at NASA to discover ways to use quantum computing to optimize the spacecraft route, to simulate more complex systems, for example, the propulsion systems, and to process and interpret a vast amount of data received from space observatories and space missions. To work on the last mentioned, the next generation of D-Wave and D-Wave 2X will be used by NASA in cooperation with companies like D-Wave and Google to optimize the problems. This is one of the first times using a commercial system in scientific research. The capabilities of classic computers in the execution of tasks of a similar nature may not exceed the issue at hand. Quantum computer theorists, like intractable but quantum computing theory, suggest that instead of intractability, such problems are reducibility arranged. It is also the main part of machine learning, cryptography, and material science for the progressive science community. Despite all the promise, quantum computing remains in the early stages and still faces significant hurdles. A few of these are high error rates, environmental decoherence, and scaling systems up with lots of qubits. However, challenges such as these do not go unseen, and companies such as NASA, in cooperation with industry giants such as Google and D-Wave, have recognized these issues and are tackling them. Other examples include Google's Sycamore processor, which in 2019 achieved quantum supremacy by completing in 200 seconds a task that would take the fastest classical computer thousands of years. They pushed the envelope in quantum algorithms and hardware, unlocking a future wherein quantum computing completes the pantheon of tools available to scientists, so they may finally find solutions for the biggest challenges confronting humanity. Quantum Artificial Intelligence Laboratory. The Quantum Artificial Intelligence Laboratory, or Quail, was established by NASA in 2013 as a pioneering initiative to explore the potential of quantum computing in solving some of humanity's most complex challenges. Based at the Ames Research Center in Silicon Valley, Quail is at the forefront of integrating quantum technologies into NASA's mission objectives. Its primary focus is to develop quantum algorithms and applications that can address problems in science, engineering, and space exploration. This collaborative hub brings together experts from academia, industry, and government to ensure that NASA remains a leader in cutting-edge quantum research. One of Quail's most notable accomplishments is its partnership with technology giants like D-Wave and Google. These collaborations have allowed Quail to study quantum optimization and machine learning techniques that could revolutionize mission planning and data analysis. D-Wave's quantum annealing systems, such as the D-Wave 2X, have been pivotal in solving problems like satellite scheduling and resource allocation. These advancements have provided NASA with new tools to streamline operations, reduce costs, and improve the overall efficiency of its missions. While Quail provides numerous operational benefits, it also enables new data analysis and modeling capabilities. Recently, these methods, known as quantum-enhanced machine learning, are being used by Quail to analyze and interpret enormous datasets, ranging from images of the early universe produced by the James Webb Space Telescope more effectively than ever before. This allows for better detection of distant celestial bodies and the ability to study their characteristics, opening up new realms of knowledge about the universe. Quail's simulation of complex systems, spacecraft propulsion, exobiological environments, etc., enables improved strategic, longer-range planning of missions related to the human exploration of other worlds. Quail has been a catalyst in this revolutionary technology, and put NASA in the lead in the global quantum computing competition. Quail is indeed a collaborative effort, and by sharing its work openly and collaborating with others, it not only advances NASA's goals, but contributes to the broader efforts of the scientific and technical enterprise. More importantly, that pragmatic sensibility emphasizes the practical advantages of quantum computing and points out have been projected for the not-too-distant future, with efforts up toward real-world innovations that could alter the future of not just scientific investigation, but even space exploration as a whole. Quail is one of those major special programs with the objective of NASA to make the most of advanced technologies to serve the well-being of humankind by using quantum computing. Quantum optimization for mission planning. Quantum optimization has become a transformative tool in NASA's quest to address the complex logistical challenges inherent in space exploration. Traditional methods of planning spacecraft trajectories, allocating mission resources, and scheduling operations are computationally demanding and often time-intensive. By leveraging quantum computing, NASA can approach these problems in fundamentally new ways, enabling faster and more precise solutions. Quantum systems use qubits that operate in superposition, allowing them to explore multiple solutions simultaneously, which significantly reduces the time needed for optimization tasks compared to classical computers. One of the primary applications of quantum optimization in mission planning is the development of efficient spacecraft trajectories. For missions to distant planets or other celestial targets, minimizing travel time and fuel consumption is critical. Quantum algorithms can evaluate countless trajectory possibilities in parallel, identifying the optimal path with unprecedented speed and accuracy. This capability not only reduces mission costs, but also increases the likelihood of mission success, particularly for long-duration and high-stakes projects such as Mars colonization or asteroid mining. Another use case where quantum optimization shines is in resource allocation. NASA missions often require the coordination of a multitude of resources, from operating satellite networks to organizing rover operations. Such tasks involve solving complex optimization problems that classical systems find difficult to do efficiently. Through its collaboration with D-Wave, NASA has been able to leverage quantum annealing technology to improve satellite scheduling and resource allocation. These advances are part of a growing prototype of quantum computing in a real-world environment that has enabled seamless data collection, minimized operational conflicts, and enhanced mission efficiencies at both ATS and SCI. This innovation will position NASA toward increasingly autonomous and adaptive missions shortly thanks to quantum optimization. Deep space exploration poses certain challenges. Communication delays render real-time guidance from Earth impractical. Quantum systems can handle, process, and analyze massive amounts of data in real time, which allows spacecraft to derive autonomous decisions that can be made in the present time in response to changing conditions. This detection capability will be critical for future missions designed to inspect distant planets, moons, and beyond. NASA's integration of quantum optimization technology with its mission planning not only streamlines current operations for improved efficiency, but also heralds a new age of exploration at the limits of scientific and technological feasibility. Search for exoplanets. Quantum computing is revolutionizing the search for exoplanets by enabling the rapid analysis of massive datasets collected by advanced telescopes, such as the James Webb Space Telescope, or JWST. Detecting exoplanets often involves identifying subtle changes in starlight, such as periodic dimming, caused by planets passing in front of their stars, or small gravitational wobbles. These signals are faint and frequently obscured by noise, making their detection a computationally intensive task. Quantum computing, with its ability to process information in parallel states, allows researchers to sift through these datasets with unmatched speed and precision, enhancing the likelihood of discovering new worlds. One of the key contributions of quantum computing in exoplanet research is its impact on data modeling and analysis. Quantum-enhanced machine learning algorithms can process and interpret complex patterns in observational data, isolating signals that indicate the presence of exoplanets. These algorithms excel at identifying subtle features that traditional computing methods might overlook, such as minor fluctuations in a star's brightness or spectral anomalies that hint at planetary atmospheres. This capability significantly expands the scope of exoplanet detection, including the identification of smaller, Earth-like planets in the habitable zones of their stars. Even beyond detection, quantum computing is revolutionizing the way scientists examine exoplanetary atmospheres, a key aspect in evaluating their capacity to support life. Quantum systems, it reveals, simulate elaborate chemical interactions and light-absorbing processes, inferring the makeup of faraway atmospheres. Such information can help identify key biomarkers, like oxygen, methane, or water vapor, which are signs of possible life. This level of accuracy is only achieved with quantum algorithms, enabling a rich understanding of the conditions that exist in these distant environments without stepping foot through the smoke and gas bubbles of the cosmic maelstrom. While this quantum process allows us to search for exoplanets faster than ever before, the broader implications reach far beyond scientific discovery. The search for planets that could harbor life might reshape the very distant future of the human race. Whether, for instance, we will one day colonize a planet other than Earth. Article Advanced quantum computing lies the outer limits of space exploration. Quantum computing is pushing the boundaries of deep space exploration as it enhances detection and analysis capabilities, allowing researchers to analyze exoplanets more quickly and with greater accuracy. NASA is not the only field in which pushing the boundaries of technology frays the edge of understanding, including our understanding of our place in the universe. As quantum computing continues to evolve, this ability will only further increase in utility, leading to a fascinating area to investigate how we could eventually reach even the farthest of planets. While quantum computing pushes the boundaries of discovery, its journey takes a turn that few are prepared for. Cybersecurity risks of quantum computing. The rise of quantum computing introduces significant cybersecurity risks that could upend the current foundations of digital security. At the core of these risks is the ability of quantum computers to break widely used encryption protocols. Public key cryptographic systems such as RSA and ECC, which rely on the computational difficulty of factoring large integers or solving discrete logarithms, are the backbone of secure communication, financial transactions, and data storage. Quantum algorithms, such as Shor's algorithm, can solve these problems exponentially faster than classical computers, potentially rendering existing encryption methods obsolete. The implications of these vulnerabilities are vast and alarming. Sensitive information, ranging from government secrets to personal financial records, could be decrypted and exposed if intercepted by an adversary with quantum capabilities. Military communications, state secrets, and critical infrastructure could become targets, jeopardizing national security. This quantum threat extends to everyday digital transactions as well, such as banking, e-commerce, and healthcare systems, which rely on encryption to protect user data. Without a transition to quantum-resistant cryptography, the global digital infrastructure remains perilously exposed. In response, post-quantum cryptography, or PQC, is the area of study whose goal is to create cryptographic systems that are secure against both quantum and classical computers and can interoperate with existing communications protocols. Entities such as the National Institute of Standards and Technology, or NIST, are leading efforts to standardize PQC algorithms, facilitating a transition to quantum-safe systems. It is, however, a massively difficult thing to do over the enormous and varied makeup of our global digital infrastructure. The challenges of legacy systems, limited resources, and uncertainty around quantum computing timelines all add to the difficulty in implementing quantum-resistant encryption. In addition to the technical risks, quantum computing poses ethical challenges around equitable access to technology and its abuse. Countries or groups with advanced quantum technology may have outsized advantages, deepening international insecurity and inequality. That means what is increasingly a malicious actor could leverage quantum technology for industrial espionage, data breaches, or even cyber warfare, throwing international stability at risk in the process. With the quantum era dawning, it is vital to develop sound governance models, foster international cooperation, and invest in defense development to counter the cybersecurity threats of this paradigm-shifting technology. We can not only embrace the promise of these technologies, but also ensure a secure and equitable digital future in the quantum age by being proactive about these challenges. Role of ethical hackers in the quantum era. Ethical hackers play a critical role in the quantum era, acting as the first line of defense against emerging threats posed by quantum computing. As this powerful technology advances, it creates vulnerabilities in digital systems that ethical hackers are uniquely positioned to identify and address. These professionals use their expertise to simulate attacks on existing encryption systems, testing their resilience against quantum capabilities. By uncovering weaknesses, ethical hackers help organizations and governments prepare for the challenges of a post-quantum world, where traditional cybersecurity measures may no longer suffice. One notable example is ethical hacker Ryan Montgomery, who revealed alarming vulnerabilities in NASA's quantum computing systems. Montgomery's investigation uncovered that during routine simulations, NASA's quantum computer inadvertently breached top-secret encryption protocols, gaining access to classified government databases. This revelation underscored the unpredictable power of quantum technologies and the potential risks of deploying them without adequate safeguards. Ethical hackers like Montgomery not only expose these vulnerabilities, but also highlight the urgent need for quantum-resistant encryption and more robust cybersecurity frameworks. In the quantum age, ethical hackers play a pivotal role in helping lead us into post-quantum cryptography. While some organizations, such as the National Institute of Standards and Technology, or NIST, are attempting to standardize quantum-resistant algorithms, the promotion of quantum-resistant encryption led to significant testing and validation. So how do ethical hackers contribute? By stress testing these new systems to make sure they are secure against classical and quantum threats. Their proactive approach helps foster confidence in emerging technologies and prevents risks from being exploited before they can by malicious actors. Ethical hackers work as strong advocates for responsible quantum technology development beyond technical touchpoints. They highlight the ethical concerns with quantum computing, including the risks it poses to increasing already large socio-economic divisions, and the risk of it being used for cyber warfare or espionage. Through facilitating conversations between technologists, policymakers, and the public, ethical hackers contribute to establishing governance structures that ensure that quantum technology is developed and utilized safely and equitably. The quantum era is upon us, and their contributions will help ensure that the world can secure itself against any nefarious actors, and that the power of this transformative technology can be used for good. Quantum technology in deep space. Communication. Quantum technology is poised to revolutionize deep space communication by addressing the significant challenges of maintaining secure and reliable connections across vast distances. Traditional communication systems face limitations in bandwidth, latency, and susceptibility to eavesdropping, especially as humanity ventures deeper into space. Quantum advancements, such as quantum memory and quantum networks, offer solutions that could enable ultra-secure and efficient communication channels between Earth and spacecraft. These innovations are not only essential for protecting sensitive mission data, but also for advancing the scope of space exploration. NASA's work on quantum memory is a pivotal development in this field. Researchers at NASA's Glenn Research Center, in collaboration with Inflection Inc., recently developed a quantum memory system capable of storing information in a cloud of atoms. This technology allows for the preservation and retrieval of quantum information over time, an essential feature for establishing large-scale quantum networks. These networks could synchronize and distribute quantum information across vast distances, enabling secure communication channels that are resilient to hacking and data interception. The deep space communication environment is one of the most difficult fields of human exploration, yet communication over entanglement is one of the most effective research fields of quantum technology that will translate into enhanced data transmission in deep space communication. Quantum entanglement involves the ability of two or more particles or qubits to remain interdependent, even if they are separated by large distances, such that the state of one particle can instantaneously change the state of the other particle. The no communication theorem, however, also implies that while entanglement cannot be used to send information faster than light, it can be used to set up ultra-secure communication channels. This technology could be particularly helpful for deep space missions to farther away planets or places beyond the solar system, for which standard communication is affected by all kinds of lags. Data security and improved mission coordination across long distances could help NASA achieve this better decision coordination. Beyond the actual communication advances, quantum technology can also enable new tools of scientific discovery for deep space missions. Thus, quantum-enhanced sensors and communication systems could improve the detail of data captured in missions, facilitating more precise detections of gravitational waves, cosmic microwave background radiation, and beyond. Integrating secure quantum channels would also protect mission-critical data and discoveries from being compromised. NASA pushes the boundaries of deep space exploration further every year, and quantum technology will be crucial to meeting the challenges of communications in deep space and breaking new ground for human understanding of the universe. In the realm of quantum technology, a new perspective concerning deep space communication is offering the possibility of interplanetary internet infrastructure. Today's systems rely on delayed radio transmissions to send data, but quantum technology will create a seamless network threading through spacecraft, space stations, and planetary bases. Indeed, device development, such as quantum repeaters, might wire our solar system in a communications web with greatly reduced latencies and integrity on your transmitted data. In addition, quantum technology has been deployed in small satellite space missions, which stands against cultural ideas of competing for space rather than collaborating in it. The future of humanity is in the stars, as the physicist Michio Kaku writes. Through the quantum leap, we push the technological frontier, yes, but also partner more broadly in the emergence of an ultra-graded, secure, and interconnected trust-based spacefaring civilization. Unexpected consequences of advanced computing. As advanced computing technologies like quantum computing become more powerful, they introduce a range of unexpected consequences that extend far beyond their intended applications. These systems, designed to revolutionize fields such as cryptography, optimization, and data analysis, sometimes produce outcomes that challenge existing theories and frameworks. For instance, NASA experienced an unforeseen issue when its quantum computer produced results that were inconsistent with known physical laws. This prompted the organization to halt operations and investigate the anomalies, showcasing the experimental and unpredictable nature of advanced computing. One of the most concerning consequences is the potential for these systems to inadvertently compromise security protocols. Ethical hacker Ryan Montgomery revealed that during a routine test, NASA's quantum computer unintentionally accessed classified government databases by breaching top-secret encryption protocols. This event highlighted the risks of deploying powerful technologies without fully understanding their capabilities or limitations. The incident raised questions about the control and governance of quantum systems, emphasizing the need for stricter safeguards and more thorough testing. Another unintended consequence of advanced computing is the potential to disrupt existing infrastructures. For instance, the quantum computer, although capable of solving problems that are infeasible for classical systems, makes it a threat to some encryption methods meant to protect systems of finance, personal data, and other critical infrastructures. Unintended consequences of such breakthrough may, therefore, destabilize global security, with governments and organizations scrambling to implement quantum-resistant solutions. These risks highlight the tension between innovating and ensuring that it is deployed responsibly. Advanced computing promises to address some of the greatest challenges humanity faces, but its unintended consequences tell a cautionary tale about the importance of ethical considerations and foresight. The possibility of malicious uses of quantum technology for espionage or cyber attacks adds another layer of complexity to the landscape. These unforeseen effects underscore the need for robust governance frameworks, interdisciplinary collaboration, and a commitment to responsible development. With each new boundary that we push with computing, we need to anticipate and mitigate the unintended consequences of those advancements so that they are ultimately beneficial to society. Another new angle to think about is how emerging computing technologies, for example quantum computing, might fundamentally change social norms and ethical lines in ways that we cannot predict. As an example, advancements in quantum technology could challenge some of the long-standing tenets that we have related to privacy and ownership, as their ability to process and analyze massive quantities of data may result in levels of surveillance never before seen. In some cultures, where privacy is to a large degree cherished and safeguarded legally. Such developments may meet resistance or even redefine the meaning of privacy in a hyper-connected world. In addition, these technologies may magnify existing biases in artificial intelligence systems, since quantum-enhanced algorithms could inherit and magnify weaknesses in the datasets used to train them. Tackling these issues could not just be lofty technical challenges, but more multidisciplinary with ethicists, sociologists, and policymakers, so that these powerful tools are executed in ways consistent with our values and priorities. Beneath the surface of quantum progress lies a challenge that could reshape the future in ways we never anticipated. Socioeconomic divide in quantum technology access. The rise of quantum technology is set to redefine industries and scientific exploration, but it also risks widening the existing socio-economic divide between nations and organizations. Quantum computing requires substantial resources, including advanced facilities, skilled personnel, and significant financial investment. Wealthier nations and tech giants that can afford these investments are likely to gain disproportionate advantages, leaving smaller nations and organizations struggling to compete. This disparity could create an imbalance in technological power, where only a select few have access to the benefits of quantum advancements. One of the most pressing concerns is the potential for quantum technology to deepen inequalities in access to critical resources and opportunities. Organizations like NASA, in collaboration with companies such as Google and D-Wave, are at the forefront of quantum research. While these partnerships have led to groundbreaking innovations, they highlight the concentration of quantum expertise and infrastructure within a limited number of entities. Developing nations and smaller organizations often lack the means to participate in this rapidly advancing field, potentially excluding them from the technological and economic benefits quantum computing offers. The socio-economic divide further applies to the misuse of quantum technology in ethical dimensions. Rich nation-states and private industries with sophisticated quantum capabilities might exploit these technologies in pursuit of competitive advantages in trade, national security, and market fairs. In contrast, less well-resourced areas might continue to be subject to the destabilizing effects of quantum breakthroughs, like vulnerable or compromised encryption systems and inequitable access to secure communication networks. Such an imbalance begs the question of justice and fairness when considering how quantum technologies will be deployed globally. On the other hand, one question this analysis raises is exactly how quantum tech could spur collaboration between countries and organizations if this field is approached as a global endeavor rather than a geopolitical sprint. The European Council for Nuclear Research, or CERN, which brings together thousands of scientists and research institutions from around the world to achieve common goals in particle physics, is one such initiative that could be emulated in quantum technologies. Developing international mechanisms for research and resource sharing would enable resource-limited countries to both contribute to and derive gains from advances made by the global community. Moreover, promoting open-source platforms and publicly funded quantum research might democratize access to this game-changing technology, enabling smaller organizations and under-resourced nations to engage meaningfully. Thus, this method not only reduces the potential for an uneven technological field, but also emphasizes that international cooperation can expedite advances while closing wider inequalities in social and economic life. Thanks for watching. If this story blew your mind, let us know in the comments. We'd love to hear your thoughts. Don't forget to hit that like button, subscribe for more eye-opening content, and turn on the notification bell so you never miss an update. And before you go, check out the next video on the screen. It's one you won't want to miss. See you in the next one.